So in this video, I want to work through an example of the Maclaurin expansion. This could be Maclaurin polynomials, Maclaurin series, depending on how we're going to think about it. In general, it's a Taylor expansion around the variable being equal to 0. So if we're trying to address such a problem, it's very helpful to write out the formula at the beginning. And I'm doing it here for a Maclaurin polynomial of degree n, and it is a polynomial in x. So we have here x squared, x cubed, up to x to the n, and the function here is evaluated at 0, so this is a number. It does not depend upon our variable x. This is the first derivative of the function, but then with x evaluated at 0, so x here is replaced by 0. So this is again a number. So again we see that it's constant plus x times a number. The number may of course be 0. Plus x squared times another number. The second derivative evaluated at 0 divided by 2 factorial. Plus x cubed times the third derivative evaluated at 0 over 3 factorial, all the way on up to x to the n times the nth derivative evaluated at 0 divided by n factorial. To look at a specific example, I've chosen this function. So our function is 1 over 1 minus x, and in a moment I'm going to be rewriting this as 1 minus x to the power of minus 1. Now, if we want to calculate this polynomial, what we're going to have to do is to find the function and then multiple derivatives. And our function is 1 minus x to the minus 1, or 1 over 1 minus x. And when we evaluate it at 0, what we are going to get is 1, because if we put x is naught in here, we have 1 to the minus 1. That's just 1 over 1. It's 1. Now, the way I've written it here, I'm now going to calculate the first derivative, and I can see the function. So when I differentiate it, I have my eyes on what I'm about to differentiate. And this tells me to bring the power in front, so we bring a minus 1 in front, to then reduce the power, so from 1 minus x to the minus 1 we go to 1 minus x to the minus 2, and then because we have to use the chain rule, we're going to multiply by the derivative of what is in the brackets here, and the derivative of 1 minus x is 0 minus 1, so it's minus 1, and we've got to multiply by that here. So we're going to get minus times minus, and that is of course plus. So therefore the first derivative evaluated at 0 just means we evaluate this as x is 0, so it's plus, and then it's 1 divided by 1 twice, so it's 1 divided by 1 squared. It is, in other words, 1. And now we just repeat what we're doing. So we look at the first derivative, we differentiate that again to get the second derivative, and we're going to get a minus 2, and then we have 1 minus x, and we reduce this power of minus 2 by 1, so we have minus 3, and then from the chain rule we again multiply by the derivative of 1 minus x. That is again going to be a minus sign that we have to multiply all of this by, and that gives us plus 2. So the second derivative evaluated at 0 is equal to 2. So what we are doing here is we have a column in which we are evaluating the function and its derivatives as functions of x, and then just next to that I'm putting in x is 0, and that's giving us the factors that we are going to need in the Maclaurin expansion. And I strongly feel that structuring your work something like this is going to really help minimize the number of mistakes that you can make. So now we're going to look at the third derivative, and the third derivative is going to be, well, we're going to bring a minus 3 in front, so we're going to have minus 3 times 2, so there's a minus sign, and then 3 times 2, well, that's 3 factorial, isn't it? And then we have 1 minus x to the minus 4, and then from the chain rule, we are going to multiply by the derivative of the 1 minus x here. That'll be another minus sign, and minus minus becomes plus. So we see that the third derivative, evaluated at 0, is 3 factorial times 1, so 3 factorial. And I'm not going to do it here, but you can very easily, I hope, convince yourself that the fourth derivative is 4 factorial times 1 minus x to the minus 5. And that means that the fourth derivative evaluated at x is 0 would be 4 factorial, etc. So now we can substitute these results, having seen the pattern, into this formula. And I think it's perhaps worth, just for the fun of it, noting that 2 here is of course 2 factorial, so why don't I just write it that way? And the 1 here is 1 factorial, and if you wish to, you could even write this one as 0 factorial, but I'm definitely not going to bother with that. Okay, so this tells us that the function 1 over 1 minus x has a Maclaurin expansion of f of 0 is 1, and then we add to it x times the first derivative at 0, and that's 1 or 1 factorial. I'm not going to bother writing it in the product, so we're just going to write plus x, and then we're going to get plus x squared times, and now this is 2 factorial. On the bottom we have 2 factorial, they will cancel, so we have 2 factorial over 2 factorial, and as I say, they cancel, so we just got plus x squared. And then as we carry on adding these terms on, we're going to get in a similar way plus x cubed from here, multiplied by the third derivative at 0, and that's 3 factorial divided by 3 factorial, so we'll just get x cubed. And then as we carry on, we'll get plus x to the 4th plus x to the 5th, etc. And the Maclaurin polynomial of degree n for this function is 1 plus x squared plus x cubed plus, and then at the other end it would be something like plus x to the n minus 2 plus x to the n minus 1, and now the end is in sight, it's plus x to the n, and that is the result that we wanted to obtain. Now, one could talk about this in very many ways. One could continue to talk about its geometric interpretation, which I'm not going to have time to do in this video, or you could talk about how accurate it is, what the difference is between this expansion and the function, and again, I'm not going to do that, but on the next slide I want to talk about a way we can try to slightly better understand this result by testing it. So this is the result that we've just written down, and the test that I would like to do is just to multiply both sides by 1 minus x. And the left-hand side, if we do that, just gives us 1. 1 minus x times 1 over 1 minus x is 1. What about the right-hand side? Well, the right-hand side, I've written it out here. I've added a few more terms that are just hidden by these ... dots, just some of the penultimate terms. And now we multiply all of this by 1 minus x. If you'd like to pause and do it on pen and paper, you're very welcome to. Okay, so what we do now is we multiply everything here by 1, and then we subtract all of this multiplied by x. So let's write out everything multiplied by 1, and that of course is easy. It is just 1 plus x squared plus x cubed plus etc. x to the n minus 2 plus x to the n minus 1 plus x to the n. And now we're going to subtract all of this multiplied by x. So we get x times 1, which is x. So don't forget the minus sign. So what we get is minus x, and then the next term is minus x times x, that's minus x squared. The next term is minus x times x squared, that gives minus x cubed, and so it carries on. And eventually what we're going to get is minus x to the n minus 2, minus x to the n minus 1, just so we see where this one comes from. It comes from minus x times x to the n minus 2. And then we get minus x to the n. That comes from minus x times this. And then last we get the term that comes from minus x times x to the n. And that is minus x to the n plus 1. So this is beautiful. We see lots of cancellations. The first term survives is the 1. Nothing cancels that. But we see that the plus x and the minus x cancel. We see that the x squared and the minus x squared cancel. X cubed and minus x cubed cancel. Along here, x to the n minus 2 and minus x to the n minus 2 are going to cancel. We have x to the n minus 1 minus x to the n minus 1 cancel. X to the n minus x to the n cancel. And then we have finally minus x to the n plus 1, and that has not cancelled. So let me just write that down. So our answer for the left-hand side is 1 plus a term which is of a higher power in x than where we had stopped. So what I can do down here is I can say that our answer for the right-hand side, once we've multiplied by 1 minus x, is 1 plus terms of order x to the n plus 1, and that is beyond the order of our expansion. So the fact that we get this does not show that our answer is wrong. In fact, the fact that we've got 1 plus this shows that our answer is correct. If we had 1 plus something like, say, x squared or x to the 4th, that would show that we had made a mistake. This shows that what we have done is correct to the order that we have expanded it. So rather than writing out something as chunky as this, what we do is we just say that this is 1 plus, and then it's terms of, this is a calligraphic O, x to the n plus 1. So this means that. And what we read off from this is that this is indeed equal to what we expected. So this is as expected. So one can talk an awful lot about Taylor and Maclaurin series and the level of expansion that you're going to and what the remainders are, etc. And I'm not going to do that in this video. What I would like to do instead is to talk about some extensions of this approach. Let's look at the next slide. So first of all, I have a small exercise for you. I would like you to calculate the Maclaurin expansion of this function, 1 over 1 plus x, so very much what we had before. And if you have a go at that, then I will carry on with the solution. So see you in a moment. Okay, welcome back. What I hope you have found is that the expansion for 1 over 1 plus x is equal to 1. That's what you get when x is set equal to 0. And then it's minus x. And I think the minus sign makes sense. Imagine that x is positive. Adding x to the 1 on the bottom is going to make this smaller. So therefore we have to be expecting to subtract something from the 1. And then the next term you're going to find is positive. It's plus x squared. The next one is negative, minus x cubed, plus x to the 4th, minus x to the 5th, etc. Okay, what I would like to do is just to point out that you could have written this right down immediately from our result. So let's just say why. So if you know that 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the 4th. This is the Maclaurin expansion for it. Then what it tells you is that you can write down a great many free gifts immediately. So you are given that 1 over 1 plus x, well, that is 1 over 1 minus x. So we can just take this result, and everywhere there is an x here, you replace it by minus x. So what you get is 1 plus minus x plus minus x squared plus minus x cubed plus minus x to the 4th, etc. And all we've done here is we said 1 over 1 plus x is 1 over 1 minus x. So this can be written in this way, but x is replaced by minus x. And now we just expand things, and if it's an odd power in x, you get a minus sign. So minus x, or so minus x cubed. But when it's an even power, you get x squared, x to the 4th. So what we obtain is therefore 1 over 1 plus x is 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th, etc. So the formula that I would recommend learning off by heart is this one. It's really easy to remember, and with that you get lots and lots of free gifts. And on the next slide I'm going to ask you to calculate some more of these essentially free gifts. So here are 3 exercises for you, and I'm asking you to write down, not to calculate from scratch, but to write down immediately from your knowledge of the Maclaurin expansion of 1 over 1 minus x, what the Maclaurin expansions of this, and of this will be. So if you pause the video and write them down, on the next slide I'll write out the answers. Okay, welcome back. Let's have a look at the answers. So what I'm hoping you've written down is that the Maclaurin expansion of 1 over 1 minus x squared, well, all we're doing is we're replacing x by x squared, so you get 1 plus x squared plus x squared squared plus x squared cubed. So you just write out all of this. And you see here, this is an even function. It's invariant under x being replaced by minus x because you square it. And here we only get even powers of x. Again, invariant under x goes to minus x. Here we've just got a number, 1 over 1 plus 2x. So you can think of this as being 1 over 1 minus 2x. So we get 1 plus minus 2x plus minus 2x all squared. So that gives you 4 plus 4x squared. And then it's plus minus 2x all cubed. Minus 2 cubed is minus 8. And then we have x cubed plus 16x to the 4th, etc. And then here, all we've done is we've replaced x by x to the 10th. So you get 1 plus x to the 10th plus x to the 10th squared, etc. And if you look at something like this, if you know the expansion for 1 over 1 minus x, you can write this down immediately. If you didn't know it, you could always say, well, I'm looking at 1 over 1 minus u, find the expansion in u, and then replace u by x to the 10th everywhere. So that would be u squared, u cubed, etc. It's an awful lot easier than calculating the expansion of 1 over 1 minus x to the 10th directly from the formula, because if you're going to do that, to get this term, you are going to need 10 derivatives, 20 derivatives for this. And it's really not going to be any fun whatsoever. So with that, I will stop this video.